Welcome to our video on the top 30 microservices interview questions for 2026. This guide is tailored for experienced professionals with over 5 years of industry experience. We'll cover essential architecture, design patterns, and real-life examples. Don't forget to check out our channel Zito TechVerse for more. In this video, we'll explore key pillars of microservices, from core concepts and communication strategies to resilience, data consistency, distributed transactions, security, and observability. We'll also cover essential deployment and testing methodologies. First, what is microservices architecture? It's a method of developing software as a collection of independently deployable services, each owning a specific business capability. This differs from a monolith, where the entire application is one unit with a shared codebase and database. Netflix is a classic example of this approach. How do you decompose a monolith? Domain-driven design is the key. By identifying bounded contexts, you can define natural business capability boundaries. Each of these contexts becomes a service candidate. Focus on ubiquitous language, and always split by domain, not by technical layers like controller or repository. Next, the API gateway. It acts as a single entry point for all client requests, handling cross-cutting concerns like authentication, rate limiting, and routing. It shields clients from internal service topology changes, allowing you to scale your internal services independently. Service discovery is vital. Services register themselves on startup and deregister on shutdown. Clients or load balancers then query this registry to find live service instances. Popular tools include Eureka, which focuses on availability, and Consul, which adds strong consistency and DNS capabilities. Choosing communication styles. Use REST for public APIs and simple CRUD operations. Turn to gRPC for high-performance internal calls and streaming. Use messaging systems like Kafka for asynchronous decoupling and event-driven flows. As a rule, use synchronous calls for reads and asynchronous for writes with side effects. Resilience is critical. The circuit breaker pattern prevents cascading failures. In a closed state, traffic flows normally. If failures spike, it opens, failing fast. A half-open state allows probe requests to check if the downstream service has recovered. Libraries like Resilience 4J make this easy to implement. The bulkhead pattern is another resilience essential. It isolates thread or connection pools for different dependencies, ensuring that a slow downstream service doesn't exhaust your resources and starve other, healthy parts of your system. It's essentially like compartments in a ship. One leak won't sink the entire vessel. To effectively use circuit breakers, you must combine them with timeouts and retries. Timeouts ensure you don't hang threads on slow requests. Retries handle transient failures. However, always set your timeouts first, as they are the foundation for any meaningful retry or circuit breaker strategy. Why avoid two-phase commit in microservices? Because it requires services to hold locks while waiting for a coordinator, leading to tight coupling and poor availability. If a service goes down, the entire transaction blocks. Instead, embrace the Saga pattern and eventual consistency for distributed transactions. The Saga pattern manages distributed transactions as a sequence of local steps. You can use choreography, where services exchange events, or orchestration, where a central controller manages the flow. If a step fails, you trigger compensating transactions, essentially a logical undo, to keep the system consistent. The outbox pattern solves a common problem: how to save to a database and publish an event atomically. By saving the event to an outbox table within the same transaction as your data, you guarantee the event will be published, usually by a separate relay process like Debezium. Kafka is a pillar of event-driven architecture. It acts as a durable, partitioned, and replicated log. Producers write events, while consumer groups allow multiple services to process these events in parallel. Its retention capability even allows for replaying events when onboarding new services. Finally, CQRS and event sourcing. CQRS separates your read and write models to optimize for different patterns. Event sourcing stores the state of an entity as a sequence of immutable events, rather than its current value. This allows you to rebuild state by replaying events whenever necessary. Moving on to message handling. How do you ensure message ordering and ID impedency in Kafka consumers? Use a consistent partition key, like an order ID, to keep related events ordered. For ID impedency, store processed event IDs in your database and skip duplicates. Always design consumers to be idempotent, since at least once delivery is the default. The database per service pattern gives each service its own schema, preventing cross-service joins and ensuring independent scalability. While this avoids tight coupling, it complicates cross-service queries, which you can resolve using API composition or CQRS read models. Choose the right database for each service: Postgres for orders, MongoDB for catalogs, Redis for sessions. How do you manage eventual consistency? Accept that data may be stale temporarily to prioritize system availability. Design your UI to communicate this to users, like showing, quote, order processing instead of a finalized count. Use strong consistency, only when specific business rules strictly demand it. For service-to-service authentication, layer your identity strategies. Propagate user JWTs for identity context, and use MTLS or OAuth, 2 client credentials for secure service-to-service communication. Service meshes like Istio can handle MTLS transparently, sparing your application code from complex security logic. Zero trust means never trusting, always verifying, even within your own network. Every call must be authenticated, authorized, and logged, regardless of where it originates. Combining microsegmentation, MTLS, and short-lived tokens ensures robust security, as seen in Kubernetes environments where even internal pod-to-pod traffic is encrypted. Distributed tracing is essential for modern observability. By propagating trace and span IDs across all service calls, you can visualize the full path of a single transaction. Tools like Zipkin or Jaeger collect this data, and sampling helps you keep system overhead manageable in high-throughput environments. The 3-pillar observability model consists of logs for debugging specific requests, metrics for aggregated performance data like latency and error rates, and traces for the full transaction journey. A stack featuring ELK, Prometheus, and Jaeger effectively covers these needs. Remember, metrics show what is wrong, traces show where, and logs show why. Centralized logging requires structured JSON logs with a correlation ID to filter a user's journey across multiple services. Use agents like FluentBit to ship logs to a search-enabled store, like Elasticsearch or Loki. Being able to toggle log levels at runtime without restarting services is also a valuable production capability. Deploying on Kubernetes involves defining deployments, services, and config maps for each microservice. Use readiness probes to route traffic only when an app is ready, and liveness probes to recover from failures. Rolling updates are key to achieving zero downtime, while resource limits and horizontal pod autoscalers keep your performance stable. A service mesh uses sidecar proxies, like Envoy, to manage network traffic, solving issues like MTLS and circuit breaking without adding complexity to your app code. While powerful for traffic shaping and observability, be mindful that it introduces some latency and resource overhead. For safe releases, use canary deployments to route a small percentage of traffic to a new version, monitoring its health before a full rollout. Blue-green deployments offer a quick switch between 2 full environments. Use Kubernetes labels and tools like Istio to manage these traffic splitting strategies effectively. The Strangler Fig pattern is the gold standard for monolith migration. It involves incrementally extracting features into new services while routing specific traffic away from the monolith. This minimizes risk, as the monolith serves as a fallback until the migration is complete. When versioning APIs, URI versioning like V1 or V2 is widely considered the most practical approach. Avoid breaking changes. Instead, favor additive updates. Use consumer-driven contract tests, like Pact, to catch breaking changes early, and always provide ample notice before deprecating older versions. Implement rate limiting at the API gateway to protect your system from abuse. Use algorithms like TokenBucket for handling bursts, and return a 429 status code with a retry after header when limits are hit. For internal communication, libraries like Resilience4j offer built-in rate-limiting capabilities. Effective testing follows a pyramid: unit tests for logic, contract tests for API agreements, and integration tests with real databases using test containers. Keep end-to-end tests for critical paths only, as they are slower and more fragile. Contract testing is particularly powerful for finding bugs early in the cycle. Consumer-driven contract testing with Pact helps ensure compatibility between services. In this model, the consumer defines its expectations in a contract, and the provider verifies it can satisfy that contract in its own test suite. This prevents breaking changes from reaching production and avoids the need for running complex end-to-end tests during CI. Running microservices in production brings challenges like distributed debugging across services, managing eventual consistency, handling network failures, and dealing with increased operational overhead. Being honest about these difficulties during an interview shows that you understand the reality of managing complex, distributed systems. A solid production readiness checklist includes configuring health checks, implementing structured logging with correlation IDs, setting up circuit breakers for external calls, and having documented runbooks with assigned ownership. Demonstrating this level of operational maturity is what separates engineers who just write code from those who truly own their services. Thank you for watching this deep dive into microservices. If you found these interview insights valuable, please subscribe to our channel, Zito TechVerse, for more architecture guides and career-focused content. We look forward to helping you succeed in your next professional challenge.